Hello everyone, welcome to GIA Knowledge Session. These are a series of talks and seminars about gemology that are fueled by decades of research at GIA. My name is Chunwei Zhao. I'm the Senior Manager of Pearl Identification at GIA, and I will be moderating the session today. Joined with me today is GIA consultant Nicholas Sturman. Nick has more than 30 years of experiences in testing pearls and the related materials, and he's going to talk about X-rays and their use in gemology. Before we start, just a little bit of housekeeping. Everyone is automatically muted when online. If you have any questions, please feel free to submit them through the Q&A feature at the bottom of your screen. You can send the questions anytime during the talk, and then Nick will try to answer some of the questions at the end of his talk. This session will be recorded, and you will be provided a link so that you can review the session anytime in the future. All right, so without further delay, I'll pass the microphone to Nick. Nick, it's all yours.
Okay, thanks a lot, Chunwei. You've already covered the topic of my presentation today. So what I'll do to begin with is just go through the topics within the presentation that I will cover. The first one will be the X-rays themselves. I'll look at the X-rays themselves and then look in the details like the tubes and safety. Then I will discuss the main applications in which X-rays are used in a typical gemological laboratory. However, some labs do not offer Pearl services, so this should be kept in mind. After that, I will move on to discuss some other applications that could be applied in a gem testing lab, but usually aren't because there is no need, since other tests negate the need to apply them. I will not cover X-ray applications such as X-ray fluorescence, hyperspectral mapping, particle-induced X-ray emission, X-ray phase, contrast, or techniques that require synchrotron X-ray emissions, etc. There are lots of applications when it comes to X-rays out in the wider world. Finally, I will cover a few miscellaneous points or odds and ends, but I hope you all find equally as interesting as the points I cover during the former slides. So I'm sure that the majority of you know about the electromagnetic spectrum shown here. It shows the various forms of radiation based on their wavelengths and energy. We are all familiar with the visible light between 380 nanometers and 780 nanometers, as we use white light every day of our lives to see everything around us. However, in gemology, we use everything from infrared down to the gamma rays to help in the ID of gems or to treat them. An important point to keep in mind is that we go from radio waves, but as we go from radio waves to gamma rays, the wavelengths decrease and the energy increases. This is especially important when it comes to safety. And we all know X-rays need to be treated with a great deal of respect. Actually, anything from shortwave UV to gamma rays needs respect. For example, how often have you been told to not look directly into shortwave radiation when you've been studying gemology? So yeah, it's very clear that the X-rays, this end of the electromagnetic spectrum, have a lot of energy, and therefore they penetrate matter more strongly than any of the other wavelengths that are further up. We also, it also brings me to the next important consideration when it comes to X-rays. How do X-rays and the materials being exposed interact? Generally, those that consist of chemical elements with lower atomic numbers within their composition will transmit X-rays more freely than those with higher atomic numbers. Therefore, different materials possess different X-ray densities depending on the elements they are composed of. I hope you'll see this clearly by the end of the presentation. But here is an example which will be illustrated later. Carbon has an atomic number of 6, which is well below that of zirconium at 40. So we have the carbon here at 6 and the zirconium here at 40. When both materials are exposed to X-rays, carbon allows the X-rays to pass through more freely than the zirconium. Hence, it is a very quick, albeit expensive when it comes to the equipment, way of separating the two materials. However, most of the time, we associate X-rays with those unwanted visits to doctors and dentists. I'm sure you've all been there. We don't really like to go there, but this is the sort of thing that we will see when we visited one. So, I borrowed this image from my daughter after her relatively recent motorbike accident. And you can see clearly that the metal components show up, they stand out completely from the bone and the tissue around. So you have here the metal component, you can see the screws, and there's a metal plate here, which was used to straighten her arm. And it's very obvious, and it stands out here as well in another direction. So this is what we expect to see when we use X-rays, and in the medical world, everyone knows about it. But in gemology, not so many people maybe appreciate the uses of X-rays, and that's what I'm sort of sharing with you today. So even though X-rays have been used since the late 19th century, it wasn't until 1929 that they were first introduced into a gemological laboratory. This image from 1924 here shows the type of X-ray unit available at the time. And initially, they were focused on X-ray diffraction analysis. I'll discuss this more later. There's an image here of Basil Anderson, who used to work in London in the London Chamber of Commerce laboratory as it was originally known. And he's seen using one of these diffraction type instruments or units. The pearl basically was placed on top, and the X-rays, this is the X-ray tube, this is the generator. And as you can see, safety wasn't really one of the paramount points about this type of apparatus at that time. It served the purpose, and it was initially, as I said, for diffraction analysis. So this brings me onto the tubes. So obviously an X-ray machine is more than just one component. It needs many parts to make a whole working unit. One of the most important is the X-ray tube that produces the X-rays. When they were first introduced, tubes looked like these examples, and the one on the top here, and these two more modern ones. But in brief, the tubes work by producing free electrons from a heated tungsten filament at the negative cathode. So you can see here, this is the filament area, the cathode. They are accelerated towards a positively charged anode target, which is down here at the bottom here on a metal plate. And the target abruptly stops the electrons. And as a result, X-rays are generated under the impact on the target. So from the text here, which I actually took from a website which markets these, you can see that there are different types of anode material. We have different metals that make up the anodes. And for the whole, the actual material, they have glass originally, but nowadays, as you'll see later, they don't really have glass so much. But these tubes can still be used, purchased and used nowadays. But as I said, this is more like the tube that we see today. This was actually one that we took out of one of our old units in Bangkok after it failed. They are basically just like light bulbs, only much more expensive, and they need to be replaced every now and again. these modern ones have advantages like ramping up automatically and not requiring a gradual manual warm-up period when energized. They also do not need to be water or oil cooled. They basically are a whole unit on their own, and they are very efficient modern tubes. So I mentioned safety, and this obviously, when we're dealing with X-rays, is very important. So the staff all need to be very aware of other safety aspects. And when we enter any area containing X-ray units, there are always warning signs, or you could say safety signs, on the doors to ensure everyone keeps alert. However, it is even more important when we have visitors, because obviously visitors are not so aware of what they're entering, and we have to make sure that they are safe. Any visitors who come in are safe. So these are the signs that we have on the Bangkok Pearl Department door as anyone enters in. And you can see this is a typical sort of radiation monitoring badge, sort of a warning about beware of radiation. And we also have, because we have lasers for Raman, we also have other warning signs too. In addition to the signs, we have dosimeters as well, and training is very important too. So every staff member wears one of these personal film monitors and is sent to be checked for any radiation exposure each month. Different countries have different regulations regarding safety, and some, like our Bangkok and Carlsbad locations, require all or some of the staff to sit examinations, while in New York, there is an annual safety inspection and a course that has to comply to local regulations. Another point that we see on the X-ray machines themselves is what we call these interlocks. So every one of the machines that produces X-rays has to have an interlock on it. And as I said earlier, you didn't have anything like this really on the really early machines. So here you'll see that there are these two parts of the interlock. And when the door, these are on the door, so when the door is closed, they meet this circuitry here, and it makes the circuitry complete, and therefore you can switch the machine on, you can switch the X-rays on and use it. If there's any fault and this doesn't make a connection, then you cannot use the machine. So it's very safety conscious in any lab environment. We have to be very aware of that point. And moving on to the applications in the lab, of course, I'm sure that many of you know that EDXRF is found in virtually every lab in the world, I would say. And it's very useful for analyzing the chemistry of many different materials. And here we just have a cross-section or a schematic diagram of an EDXRF machine. You can see that there's a sample wheel. We have the X-ray tube, so the X-rays are generated from the tube, they hit the sample, and then the secondary X-rays are received by the detector collimator here, and of course goes through the system to the software, etc., and then we'll see the results. So it's very important really to know that the tube and the detector, they have lifetimes and they need to be replaced every now and again. But the actual window of the detector is actually very, very fragile, and it has a beryllium window on it. And if this is broken in any time, then we have to replace the whole detector. So this is one critical factor. Here we can see that you have the inner workings, the actual X-ray tube and the detector. And this is when you open the lid, what you see, where you put the sample. The rotating wheel here is not actually in this example. Here we just put one sample at a time. So actually I borrowed this slide and the previous one from Aaron Pulkey's talk on tools of the trade, which was a knowledge session back in June last year. So if you want another explanation of this, you can listen to him. But however, in brief, the theory of XRF goes along these lines. A stable atom is made of a nucleus and electrons orbiting it. So you have your nucleus, you have your electrons. The electrons are arranged in energy levels or shells, and different energy levels can hold different numbers of electrons. When the high energy primary X-rays collide with an atom, it disturbs its equilibrium. An electron is ejected from a low energy level, and a vacancy is created, making the atom unstable. So you can see it's ejected here from the X-rays which hit it. So it's unstable, and therefore we have to restore the stability by an electron from a higher energy level dropping into the vacancy left by the original electron. The excess energy released as the electron moves between the two levels is emitted as secondary X-rays. The energy of the emitted X-ray is characteristic of the element and is collected by the semiconductor detector and showed in the last slide. Their different energies are sorted and then processed at high speed in a multi-channel analyzer. The resulting spectrum is then displayed for the user to interact with. And here we have one of the units in Bangkok being used, and it's used for many routine checks on different materials. Pearls are tested in order to determine whether they formed in saltwater or freshwater environments. When we test freshwater pearls, we expect to see higher concentrations of manganese and lower levels of strontium than we would expect to see in saltwater pearls. So it usually takes around 10 to 15 minutes or so for each run. And you can see here we have the results of a freshwater pearl. The manganese is showing at 588 parts per million, strontium at 476, where in comparison, if we check a saltwater pearl, the manganese is much lower. In this case, it's 25. So a big difference between 588 and 25. And the strontium is higher. So 1,381 versus 476 here. So this is typically what we would expect for the two. And you can see the screen here where the results are shown. And you can see that in more detail here. But as well as the pearls, as I said, we use it for many applications, and origin determination is one in colored stones, but I think you've probably all read about in various publications. Here we've had Thai ruby, and the results are showing sort of very high iron, and the chromium is in relatively lower. And you actually have the figures here in parts per million. Again, you can see that the iron is 1,182 in this example, and the chromium 746. So we know that the Thai rubies have higher iron concentrations. And if we compare that to a Myanmar ruby, we can see that the iron is much lower. So here, 46.4 parts per million, and the chromium is much higher. So we have 700 here. So it's a very useful technique to help. I mean, it doesn't prove, but it's just another piece of the puzzle to help with origin determination in corundum. And of course, the main application for me in the lab is the pearl testing side. So when we're talking about X-rays in gemology, a lot of people will associate them with the pearl testing side. I showed you this image before, of course, and you can see that a modern unit like we have here in Bangkok is completely different. The safety aspects are built into the unit. It's completely lead lined. So it's like all sort of machines which are generating X-rays and are made of sort of substantial amounts of lead. They're very heavy, so moving them around, etc., is another matter. But this is the sort of machine, as I said, we're using nowadays, and a complete contrast to what we used, what were used before in sort of 1920s, 30s, 40s. Now I'm going to preempt a potential question here, because I've been asked this on several occasions over the years, and it basically goes, can I ask my dentist to test my pearls? And the simple short answer to that is not really. While I've seen the results of such tests, the units used by dentists, like the one my dentist in Bangkok uses, as shown here, aren't really suitable because the quality of images aren't as good as the ones we use in the lab. The lab units are designed more for big volume, continuous semiconductor type operations. And as I hope you will see in the following slides, the quality of the resulting images are pretty good. So yeah, as I said, this is actually taken from my dentist website, and you can see that it's not quite the same. It's not fully enclosed. And I'm sure that when you've been to a dentist, most of the time you have to stay in the room, and the operator, the radiographer will go out and then come back in quickly after the very short exposure. So it's a bit different to the sort of x-rays we use in the lab. Another point we have to cover as far as the x-ray machine, as I said, it's made of many parts, is the detectors. So we have two types shown here, the image intensifier and the flat panel detector. So here's the image intensifier, and this is the flat panel. The image intensifiers are generally being phased out when it comes to finer detail imagery, as they are more grainy due to the difference in pixel sizes and sensitivity. The flat panel detectors are now more or less the norm. And before we had the upgrade in Bangkok, this was one of our machines which had the image intensifier in. And you can see that the result is shown over here, and you can see structure, but the flat panel detector that replaced it actually produced this image. So when you compare the two together, the details that you can see here are sharper, and the line here is much sharper. And you'll see in some of the images coming up as well, this difference. And I just increased it here for you so that you can see more clearly that boundary. So this is a bead cultured pearl, and this is the boundary where the bead is. It shows more clearly here on this image because it's the flat panel detector. And the structure here on these two parts, which are sort of grown on the surface of the pearl, are also much sharper in detail too. So since we're talking about, so taking all that I've just discussed into consideration, what can a modern X-ray unit in the lab help us with today? So we can check for the ID. We can separate natural pearls from other types of pearls. So the bead cultured, the non-bead cultured, composites, imitations, etc. We can look and see if there are any signs about the environment. So we can check for saltwater and freshwater by checking the structures of some pearls. And then there are also some treatments which we can detect, like silver, salts and fillings. And then to a degree, we can check for mollusk ID too. So this gives an example of the X-ray machine being used for a natural pearl. You can see the shape, the pearl here itself, and then you have the exact outline, and the structure internally is very clear on this one, and it shows it's basically following the shape of the pearl. So this is what we would expect to see for a natural pearl, this typical structure. And these are other natural pearl structures. You can see that they're not always the same. You'd expect to see some variation. We can have just one or two arcs with very little structure in the middle. We can have a very small organic rich area right in the center, which is typical of many natural pearls. We can have larger areas of organic matter, like these, basically these three showing sort of fairly similar materials. Or like the last one, we can just have nice concentric structure showing. Bead cultured pearls, on the other hand, show, well, as you would expect, completely different structures. So to separate bead cultured pearls from natural pearls and non-bead cultured pearls is not really an issue. It's for any lab with good equipment, it's a pretty straightforward operation. The only thing I can sort of show you here, but was interest with bead cultures, is the variation in the size of the nuclei themselves. So for example, in this pearl here on the left, we have a small bead, whereas in this pearl here, we have a much larger bead in relation to the actual volume of the pearl. Sometimes we see some very obvious organic and void areas around beads, and they often show the deformed pearls. This one here has a cracked bead, it's split in half. And we have here one pearl which is showing that it's drilled inside the bead, but the pearl is not drilled itself. I mean, the hole does not continue. So this is something else I can talk a long time about, but I know we're sort of short of time. Non-bead cultured pearls, the structures are fairly typical, and they're not always so simple, but on the whole, we see these void-like structures. This is one pearl showing a void, and then it's got this sort of organic area here. And when we increase the magnification, which we can do with these modern units, we can see the detail more clearly. Likewise, on this pearl, we have the same sort of feature, but in fact, it's got like another entity inside. And if we increase the magnification, we can see. So in actual fact, this looks like it could be an atypical bead cultured pearl. But in fact, it's not. And we've seen this quite a lot in non-bead cultured pearls. And this is a large void in a non-bead cultured pearl. And again, it's got some sort of structure within the void. So it's not like it's completely hollow. And the difference from this one over here on the left is that we have this sort of like linear type feature. And I was saying that we could separate to a degree salt water from fresh water using the X-rays. Well, this is more indicative of freshwater origin non-bead cultured pearls, whereas these larger voids are more indicative of the salt water. So we can get an idea, but we still have to prove using the other tests. And this is a sort of fairly typical appearance that we see in freshwater non-bead cultured pearls. And you can see that sort of like linear type feature, but we've also got the concentric structure too. So this is very typical and what we would expect to see. Sometimes we see pearls that show slightly different structures and they can be unique. So for example, this is the souffle cultured pearl, which was introduced in the market around 2010. And when we x-rayed them, we found that they appeared to be filled. So these are the radiographs, the microradiographs, and you can see that there's no drill hole, there's no sort of feature on the surface which would look like we had an opening that could be used to fill the pearl. And when we used the CT tomography, we could see the detail in greater detail. And you can see that this sort of structure inside is very strange. So when these were actually supplied to us for analysis, we were told that they actually used mud as a basis, as a nucleus, if you like, to produce these pearls. And then that means that when they are drilled and used in items of jewelry like these necklaces here, it's pretty obvious that that filling material is actually going to come out. And you can see the difference between the previous slide and this. Looks like there's no material inside. It's essentially they are hollow now. And that's because after the drilling, all of that material was removed. So these pearls are essentially pretty lightweight for the size compared to the actual weight when you hold them, they are much lighter than you would expect. So I mentioned fillings, although that wasn't exactly a filling, you know, and it intentionally filled to, usually fillings are made to increase the weight. This is an example of a pearl that actually was filled, and it was filled by using all these different bead cultured pearls. So you can maybe just see on some of them, like this one here, that this is a bead cultured pearl. So what happened here was originally it was a large bead cultured pearl. This is the original bead, but there was under this setting, there's an opening, and they used that opening to fill the cavity that was evident with lots of other small bead cultured pearls, and then they sealed that cavity with a design and a setting. So, you know, these are the sort of interesting things we see from time to time in the lab that clients submit to us just to check the idea. And here are a couple more. These have all been sort of shown and discussed in Journal of Gemology. So this is a hollow. You can see again the opening down here where the filling was inserted, and this is sort of all different fillings like pieces of shell, maybe some cement. And in actual fact, here there was on the CT there was actually what looked like it could be a pearl. So maybe they put some other pearls, even natural pearls, inside. Whereas this one here is showing metal wire that was actually inserted. But then this one was a very crude attempt at making a whole pearl, because they actually cut it in half, put the wire in, and then stuck it back together again. So not the best sort of deceitful pearl that's ever been created. So this brings me on to the other application in the lab that's used a lot, and that's X-ray computed microtomography. I've already shown you a few images that are produced by this unit. And unlike the RTX results I just discussed, this method allows gemologists to examine thin slices of a pearl in any given position in 3 different directions, and to obtain 3D imagery as well. It is very useful for pearls that need extra care, like the borderline natural keshi I mentioned before. Research work where better images are needed for publication, and whenever we encounter unique pearls that warrant more time. So here is an example of one of the latter. It may take some of you a while to realize what this is, and others will probably already have the answer. This pearl shown here is the one which had this structure inside. So it's with my colleague's hand for scale. And I hope that you've probably all realized by now that this is actually a shell, a small shell trapped inside the pearl. So this was the instigator of the pearl. And this was the RTX, the microradiography image. So you can see even with the RTX, it was very clear. But because it was so interesting and we realized that it was almost certainly a shell, we wanted to double check and get even clearer images. So we used the CT unit, and here we have very clearly, and we could measure the shell. So in actual fact, it's in the total, in the longest direction, it's just under 2 millimeters. So it's very small. Of course, we considered this as a natural pearl. And this is another one. So, you know, it shows you the detail that you can actually see on some of these unique pearls. It's another shell. And what we did with this one is we actually submitted it to some further analysis. We used some data processing on it using special software. And you can see that we could get the outline and the actual structure on the shell. And the 3D imagery of it showed a very nice scallop-like shell. So it can be very useful. And I would also note that here the detail of the CT is much finer. If you replay the video later and look and compare to the one I showed you earlier, the actual detail of this, the grain size is much finer. So this was a higher quality CT result. So the X-rays can also help us with other things apart from just the structure. So one example is that we can see the size of the drill holes, the type of drill hole, the quantity, and obviously the quality as well. And this is showing the nice natural structures, but there's one here I wanted you to see, and it shows a large drill hole, but there's a very small drill hole tagged on the end here. So in actual fact, this used to be a part drilled pearl, but actually was fully drilled later on in its life at some point and put into a necklace. And here is another example showing the same feature. You can see a very large drill hole, then a much smaller drill hole. So, you know, as I say, it's not just structures, there are other things which can help us as well. Also, we can see about this type of drilling. This is a Chinese drilling. It's also, so I've heard, being called Mandarin, they've been called Mandarin pearls too, because originally they were drilled in China by the emperors, and they were used on clothing. So instead of buttons like we use today, they actually use pearls as buttons. And in order to secure them on the clothes, they would actually drill, you can see here, one drill hole here, and then another one at an angle, so that they could actually thread the thread through here and attach it to the clothes as a button. And we have the three different directions here. And this is obviously Queen Elizabeth. It has, at the time that this drilling was used, it was obviously the emperors in China, but the royal families of Europe and the Maharajas of India, all of the sort of royal families around the world, up until the cultured pearls were introduced, were using natural pearls as buttons. And then you can see here that the clothing here has a lot of natural pearls sewn onto them. Another thing that we can look for, as I said, is the size of the drill hole. So here I just put some red arrows, and you can see that when we compare the size of the drill hole to this, and then we magnify it, this drill hole is pretty big. And this is actually a freshwater non-bead cultured pearl, which was submitted in Hong Kong very recently. And the structure is fairly typical, but one feature that you often see in non-bead cultured pearls or bead cultured pearls is the fact that the drill holes are larger than you would expect to see in a lot of natural pearls, because they're trying to save the weight, retain the weight in natural pearls, obviously to sell for a higher price, because the more pearl you lose, the less money you will get eventually. Another interesting example of what we can see of X-rays is the drilling in this particular pearl, or these two particular pearls. This one here shows a bead with multiple drill holes, and this one also shows a bead with two drill holes and also a piece of metal that broke off during the drilling process. So what is the cause of this is the fact that the bead is not fixed inside the pearl, so it's able to move around. And as the driller was trying to drill the pearl, the bead is moving around, and that's why there are so many holes. So you can imagine the fun that the driller had, and then later the fun that a stringer will have trying to restring any necklace where you need to put these two pearls in. So it is interesting to see what you find with X-rays. And I mentioned the quality as well. The quality of the nuclei used is also a factor that we can see with the X-rays. So these beads show obvious lines running through them in many directions, and these actually are most likely parasite tubes in the shell nucleus, which was used. So they're probably not the greatest quality shell nuclei that you can see in the market. Whereas maybe something like this one here is much clearer. It's much better quality. There's not really much in the way of sort of structure running through it. And this particular pearl here is showing the structure, what we call laminated bead structure. And this article, if you want to check more about the sort of laminated nuclei used, this is actually in one of the recent G&Gs, so spring 2020. And this is a cross section of the bead, and you can see that what it is a shell nucleus that was constructed by using several smaller pieces and then combined together, and then the bead was cut from that. So it's like a composite bead nucleus, and you can see it very clearly on these X-rays. When the boundary lines up with the direction of the X-rays exactly, we can see it as a very strong line. When it's slightly out of alignment, it shows like this. So this is something which we see from time to time in bead cultured pearls. And another routine type of analysis we do in the lab, of course, for pearls is to check the fluorescence. We have an X-ray unit which just checks to see whether the pearls react to the fluorescence of the unit or not. And we can see, for example, two pearls down here. This is a freshwater one, completely freshwater, so like a Chinese pearl, non-bead cultured. And when we expose it to the X-rays, we can see that it fluoresces and gives off a pretty strong fluorescence all over the surface. This, on the other hand, is a bead cultured pearl, and it's salt water, but inside there is the freshwater shell nucleus, and the freshwater shell nucleus obviously fluoresces just like the freshwater pearl here. So that's why we can see down the drill hole the fluorescence. If it wasn't drilled, you would see this sort of fluorescence as well, because the fluorescence cannot travel up the drill hole. But it's most important or most useful when we have multiple pearls in an item. So you can see here this necklace, and it's got a large quantity of pearls. So it would be very difficult to do EDXRF analysis on every single pearl. It would be very time consuming. So X-ray fluorescence is the best way to do it, to have a quick check. And we can see that one pearl stands out completely from all the others. So this particular pearl, when we actually align it with the necklace, we can point out that this is a freshwater pearl in the necklace. But the X-rays that we check, when we check the RTX unit, we will be able to only then test to see whether it's a natural freshwater pearl or a non-bead cultured freshwater pearl or a bead cultured freshwater pearl. So it just tells us the environment, but it doesn't tell us the result. This is a quick example I just keeping here to show you of an atypical bead cultured pearl. So like the bead cultured pearl I showed you before, which fluoresces, this is actually a saltwater pearl that was grown around a non-bead cultured pearl, freshwater non-bead cultured pearl that was used as a nucleus. So they inserted that into a Pinctada maxima in this case, and grew a pearl around that cultured pearl. This is a golden one as well, showing, so it's very clear to see the difference between the original pearl used here and then the overgrowth of the gold lit Pinctada maxima. And when we X-ray, do the X-ray fluorescence externally, you would see here it's fairly strong fluorescence as you'd expect for freshwater. But when we cut the pearls in half, you could see that the fluorescence of the inner part where the freshwater nucleus is shows very strongly, but the saltwater disappears. There's no reaction, as you would expect. Sometimes, though, we get atypical fluorescence as well. So this example shows you very clearly that it's not producing the usual green, yellowish green fluorescence that we expect. There are areas which are very strong orange. And recent research from the Pearl team, GIA Pearl team, and of course there are other researchers around the world who have done this as well, associate this more with vaterite, one of the calcium carbonate polymorphs. And this nectus also was interesting because it showed pearls where there were 2 nuclei in one pearl, so like a double nucleated. And the matter of treatments is also worth mentioning here, as it leads me on to the next part of the presentation, which will focus more on diamonds and colored stones. So microradiographs can also help gemologists tell whether some pearls have been treated using inorganic metal salts like silver nitrate to modify their color. This usually has to be confirmed by ADXRF analysis to make sure that the silver is fairly homogeneous across the entire surface and isn't the result of metal contamination from the setting. This is especially true of pieces that are antique, because over time there could be sort of leaching from the metal into the pearls. So you can see in this example here where the arrows are that there's a very fine white line, and this is the deposition of the silver in the structure of the pearl. You can see it here on these 2 images as well. I mean, the pearl in itself looks treated because you can see color concentrations on the surface as well. But the RTX helped to confirm that it was treated as well. So moving on to the colored stones. So we deviate from them for a little bit, but they may feature again later, so don't worry. Many of you will know that diamonds are treated in a variety of ways, and one is the filling of fractures by glasses containing various metal elements like lead or bismuth. We can usually identify these easily with the loop or the microscope in the lab. I mean, all you have to do is, I think most of you know, just to look at this with a loop, and you see these very strong colors. And then if you adjust them, you see the flash effect. This is typical of fracture filling in diamonds. And so really, there isn't really need to do any sort of advanced type of testing. But as we have an X-ray machine in-house, why not check and see? So this is what we expect to see in fracture-filled diamonds using various lead or various metal-filled glasses, if you like. So these stones are all pretty small, as you can see, but the fracture filling, these white lines, of course, as I discussed before, you know, are associated with the metal deposition in the fractures. They don't allow the X-rays through, so it's very easy to spot such fracture-filled diamonds. And of course, it's good to do the analysis in more than just one direction. We do all pearls in definitely at least 2 directions, but when it comes to anything under X-rays, it's always good to check in more than one direction. And here we can see the same stones turned so that we're going from looking down the girdle, and you can see again the fracture filling showing very clearly in them. So a useful test, but not really necessary in the lab, because most of these fracture-filled diamonds are easy to spot. However, there are some cases that are submitted to GEM labs, and if the senior diamond graders, because they're usually submitted for diamond grading and not necessarily for diamond identification, if they do spot something, then it gets changed to identification. It's not graded. But if they have any doubts about a stone, because obviously there are certain ones which are borderline, and in those cases, we do sometimes get a visit from the diamond grading department, but it is very rare. And of course, I'm talking about fracture filling, then you know that I'm going to move on to rubies probably next, and that's exactly what we're doing here. We have a few stones showing, including a star stone here. And it shows very clearly that when you X-ray them, we have that again, the radio opaque areas within the fractures, and even some surface cavities or even around inclusions. You can get bubbles trapped in the stones as well, and they have lead or bismuth around them. So it shows very clearly on these results. And again, most of the time in the lab, we don't need to test this because it's easy to spot, again, with flash effects and bubbles, etc. So it's not something we see too often, but it can be used, as you can see here, to get an idea or gauge the degree of fracture filling. And sometimes that's helpful. And we will sometimes get a visit from a colored stone department to ask, just to check to see how much fracture filling is showing in a particular stone. Most of the time, though, as I showed you earlier, we rely on EDXRF as well as the loupe and the microscope. And the results that we would get for a lead glass filled ruby would be something like this. So we would have very strong peaks relating to the lead content. So as I said, it's relatively straightforward in a lab to test this material. I thought I would also share some images of different types of material that can be used to imitate diamond, and again, what we would expect to see if we place them under X-rays. So we have diamonds, a synthetic sapphire, glass, YAG, CZ, and GGG here, and you can see the relative X-ray transparencies, if you like, to the X-rays here. The diamond, as you expect, is being pure carbon, is going to let the X-rays through readily, whereas GGG, it doesn't allow them through so easily. And this relates to the chemical composition, as I said before. So carbon with 6, and where if you compare to gadolinium garnet, you have much higher atomic numbers here. Just this is a crude sort of idea to show you the degree of opacity to X-rays, and so you can see it sort of relates as well to the image here. And what about for colored stones? I mean, is it interesting or useful for colored stones? Well, yes, you can see that there are some different colored stones here and one colorless one here, but are showing different degrees of density, X-ray density. And this is the interesting point, because you probably were thinking, well, those are all stones which are whole stones like an emerald or a natural sapphire. But in actual fact, all of them that I showed are composite stones. So when you see in the face up direction, it wasn't so easy to see. But when you turn the stone sideways, you can very readily see the differences in the X-ray transparency of these materials. So here, for example, in this synthetic spinel triplet, there is a central material which is opaque to X-rays, whereas the spinel, synthetic spinel either side, allows X-rays to pass through more readily. So it can be useful, but again, in the lab, there's no need to really use X-rays to test this type of material, because the gemologists would have identified them before there's any need to. But I just included them here just to show you the difference and the interesting results we would get using X-rays. Also, this is something which is quite interesting, because we know that when we look at inclusions within stones, we can get an idea from the crystallography of inclusions, or the difference in the refractive indices of the host material to the crystals, as to maybe some idea of what the crystals could be, their identity. But in this particular stone, I decided that it would be interesting to take it and X-ray it. And you can see that all of these crystals, when we increase the contrast, show up as very obvious opaque areas within the stone. So obviously the element within these crystals must be pretty high, and there must be a high atomic number in the structure of these crystals. So you probably have an idea of what these are already without me telling you. But there's also this area, which is interesting to note. On the stone, it's sort of a more transparent zone, and you can see it showing here that there isn't really much in the way of crystals. And again, they're sort of like a crystal-free zone. So it's a very useful, quick test. And when you look at the stone in more detail under the microscope, you can see the crystals here more clearly. And in actual fact, we actually analyzed these 3 crystals with Raman too afterwards. So just to make sure that we're not just checking by X-rays, you can see that the results showed that it was zircon. So of course, zircon has zirconium in it, and that's why the crystals were showing as opaque spots on the X-rays. So this leaves me to the X-ray powder diffraction. So this is a test that was used in the past. It's not really used so much these days in this format anyway, because the actual team in Carlsbad, I asked them if they could take pictures of this. They actually had to find the unit in the museum and bring it out to photograph for us today. And you can see that it's the Derbyshire camera. It has an inner area where the sample is set up in the center. It has to be set up as a very fine spindle. The X-rays will pass through the collimator, pass into the powder within the spindle. So we have to take the powder sample from a mineral. And then the results are collected basically on film like this. So we actually have to go into a dark room, load the camera with this film, and then submit it to X-rays for a few hours. I think it was around, from memory, about 3 or 4 hours for a run. And the structure of the crystals, when they aligned to Bragg's law, they would actually show these lines on the film when it was developed. And each mineral has a unique fingerprint that allows it to be identified. But it wasn't as simple as that, because you had to go to a library containing reference films. You had to try and go to a book as well and measure the lines and see which lines would fit most. Then go to the library, get the film out, and then put them on a light box and check to see whether the lines would align. If they aligned exactly in position to the reference sample and intensity, then you knew that that was a mineral. It was like the fingerprint match, and you knew that was the identity of the mineral. But today, we don't use this anymore, as I said. We use things like this, which is a modern diffractometer for X-ray powder diffraction techniques. So, oops, sorry. We have a detector here. We have the X-ray source again, and the sample stage. So the X-ray will pass through, hit the powder in the sample stage, and be diffracted again to the detector. And so eventually, when you look at the monitor, you would see that you would get patterns relating to the mineral being identified. And this is just the examples of the stage here, the actual sample stage. This is the holder where the powder is placed, and the X-rays obviously pass through and hit the sample here. If we wanted to, we could test single crystals. It's not only confined to powder diffraction, but you would need to set up different parameters and change the stage to a Gandolfi stage. This actually spins around here, and the crystal stays exactly in the center, in a line with the X-rays, and again, diffracts the X-rays to the detector. And what we get is essentially something like that. When we look at the monitor, we get the spectrum of the mineral, and then the red lines are from the library, and if there's a match to the main peaks, then you can check from the library which mineral is the match. So for example, on this one, it was azurite. So it can be very useful in a lab for minerals that are not straightforward to test, where you're limited with the normal tests that you see in the or are available in the lab. And going back a bit to pearls, this technique of X-ray diffraction, which we also call Lowrygram, or Lowy for short, is something that we used to apply to pearls as well. I say it's not really applied these days because we have CT and there's no need to, but it used to be used to separate bead cultured pearls from natural pearls. And if you remember right at the beginning, I showed you the very old X-ray machine. This is the type of method that was used for that machine. It would fire the X-rays through the pearl, so they would enter the pearl, and the structure of the pearl would diffract the X-rays as they pass through the pearl. So if you have a natural pearl, because they're concentric and they are consisting of pseudo-hexagonal aragonite crystals, the X-rays would pass down the C-axis of the crystals and pass through the nucleus and pass out the other side again through the C-axis, and you would get this six-fold pseudo-hexagonal related pattern. So that would tell us that in one direction, it was natural. So if we changed the pearl through 90 degrees and we did it again, we exposed the pearl again, and we got another six-fold pattern like this, we would know that the pearl was a natural pearl. However, if it's a cultured pearl, in one direction, you would get the six-fold pattern matching with the a natural pearl. But if you pass through the side, not down the C-axis of the aragonite crystal, if you pass at right angles to the C-axis through the structure, you would actually get a different pattern, and that would be this four-fold symmetry or four-spot pattern. And that was typical of cultured pearls, and it would prove that it was a cultured pearl in the time before we had good quality microradiography and tomography available to a lab. And another question that I'm probably going to preempt, so I might as well cover it here, is what happens as far as X-rays and damage to any materials? I mean, do X-rays damage any gems? So the quick answer to that is not really. On the whole, all materials that are subjected to X-rays have no change. There's no impact on them. However, conch pearls are something we have to be pretty careful of in the lab. And over the years, you know, GIA, we have our protocols. We know exactly how to handle conch pearls, so there's no harm to them when they're submitted. But if you don't X-ray them correctly, there is a chance that you can change the color of conch pearls to a sort of slightly more bluish tint. But as I said, it's something that we're well aware of, and there's no sort of real concern as far as testing in the lab is concerned. And there is also another example, usually with fresh water, but this related to the X-ray powder diffraction technique that I just shared with you. When the X-rays entered directly, because there's no gap between the pearl surface and the X-ray beam, it goes straight from the pearl beam into the pearl surface. So the area where the X-rays entered and were in contact with the pearl surface, there sometimes would be a small brown spot left. So this was something that could be related to X-ray damage. But as I said, it's not really something that is anything to be concerned about these days, because diffraction work is not used for pearls so much. So now I'm coming towards the end of the presentation, and I'm coming to the miscellaneous part. So I just wanted to include some some things here, some slides, which hopefully would be of additional interest to you all. We have a collection of shells here, they're all relatively small shells to fit in the field of view of the X-ray machine. And when we X-rayed them, you can see that they have very beautiful structures. So X-rays do reveal some amazing things when opaque items are analyzed with them. You can see the very nice structure and the typical features here towards the wall of the shell. And I put this back here so that you can get an instant idea of the shells here and the shell that we found inside that pearl that I mentioned earlier. So it's very clear to see that this is a shape that relates to the shells, and why it's pretty clear that that's the identity of what started this pearl off. And this is an item of jewelry that actually belongs to my wife. So I borrowed it from her just to create for this presentation. And you can see that when we X-ray it, we have the diamonds showing as more radio transparent. They allow the X-rays to pass through more freely than the sapphires, which although the atomic numbers in the elements making them up are not so different, there is still a degree of difference you can see between the diamonds and the sapphires. But when we place the item under long wave ultraviolet light, again, we can see that we get some reaction, and the diamonds are showing sort of a bluish reaction here. Some of them not showing so much, and this one here is showing slightly differently. And when we place under the X-ray fluorescence or luminescence, we can see that the diamonds react very strongly. So I think you can count that all of the diamonds are reacting. And this one here is showing a different fluorescence, stands out. But this is a property that is very useful when we come to another part or application of X-rays. At the diamond mines or in the diamond mines around the world, we know that a lot of ore has to pass through before any diamonds can be obtained from the ore. And so crystals like this are not found easily. So X-rays actually are used in a lot of the diamond mines, probably the majority of them. Once the ore has been crushed, you can see it's traveling here within one mine site on a conveyor belt. And then it gets to a stage where the ore has to be checked to see whether there's any diamonds in there or not. And eventually, of course, we find the diamonds like this. But during the process, it will go in the feed hopper, we have a diamond concentrate, it will go on the feed belt, and then it will be a point where they use X-rays to expose the ore that drops past the beam. And if the diamonds fluoresce, and as you can see in the slide of the brooch I showed you before, most diamonds react very well to the X-rays. The fluorescence will emit or make an air jet work here. The air jet blows the diamond off course into another bucket, and then the other ore, the sort of waste ore, is collected in another area. So the diamonds are able to be separated by using X-rays. And we have here another example showing two photomultipliers where the diamonds fluoresce, and again, the same principle is applied. So we can separate the diamonds from the tailings. So it's something that's good to see. And we also have, that was X-ray fluorescence technique, but we also have X-ray transmission. And this is from an article that I found online, and it just shows another method where the diamonds are passing on the belt, and the X-ray passed through. Whenever a diamond is detected, you can see here on the two different scans, the diamonds will show up, and therefore they can separate the diamonds from the ore. And this table shows you the complete difference of diamond transmission to X-rays relating to size and the high energy source and the low energy source. So diamonds are completely different to most of the other minerals that would be associated in the mine. And it's relatively straightforward for this type of system to separate diamonds from the ore. So it's a very useful method, and it's being employed more and more in mines today. And as far as I know, it's also been used for other gems, not only diamonds too. There's some other colored stones. So that really brings me to the end of my presentation, and no better way really to end it than to show you a watch, and again, what the X-rays can reveal when you expose the watch to them. So we have here an image showing the lighter contrast, and then when we increase the contrast, we can see even more of the structure of the inner workings of the watch. So it's certainly something which reveals the hidden nature of opaque materials. And then this is the final slide, just to give you a few references that hopefully you can use later when you replay the video if you want to go and check any articles that relate to some of the topics that I discussed in this presentation. So I hope that that's good on the time front, and I'm obviously happy to try and answer any questions you may ask.
Thank you very much, Nick. Thank you for your presentation. We don't have much time left, but I'll quickly pick a few questions for you to answer. First of all, in the lab, if there is a strand of necklace, do you X-ray every one of them?
Yes, the simple answer is yes. We X-ray every single one, because it just needs for one of those pearls to be an imitation, or I mean, we've had, for example, the necklace I showed in the fluorescence, there was one pearl only in there that was fresh water, and the others were salt water. But when we actually tested that in more detail, the freshwater one was a non-bead cultured pearl. So there was one non-bead cultured pearl. And then there were two other pearls. I didn't really have the time to sort of point them out in more detail. But for those who may be more observant, or if you want to replay the video and check later, there were two other pearls which showed very weak fluorescence as well. And those were bead cultured pearls. So in that necklace, we found one freshwater non-bead cultured pearl, and we found two saltwater bead cultured pearls, and the rest of them were natural pearls.
Okay, thank you. So how do you tell the difference between the outline of a bead or the natural growth arc of a natural pearl under the X-ray?
Well, I mean, usually if you have a bead, it's pretty straightforward, because you've got different radio opacity, even if it's slightly different within the bead itself, whereas in a natural pearl, there's a slight difference. And usually if you have what I think the question was, if you have a natural pearl and it shows a demarcation that looks like it may be a bead, there usually is some structure somewhere on the inside which would prove to you that it's not a bead. And of course, there is the point about fluorescence, which I mentioned already. There would be no reaction when we expose them to X-ray fluorescence, whereas for a cultured, bead cultured, we would find some reaction, even if it's very faint.
Okay, thank you. So why do some of the pearls show such a large space between the bead and the pearl, like a gap?
This is just during the formation, something maybe found its way, maybe the cells, the epithelial cells that were put in the mantle with the bead didn't form correctly, and it produced a pocket of organic matter rather than created a nice smooth coating of nacre around the bead. So there are various factors. So it could be even to do with the technician who did the operation didn't do something quite correctly, and it produced obviously this deformity, but produced an irregular shaped pearl as well.
Okay, thank you, Nick. We don't have much time, so I'll ask the last question right now. So someone's asking, which locations in GIA has all these equipments, the X-rays?
All of our locations have the X-ray machines. So we have Bangkok, we have Hong Kong, New York, and Carlsbad. And in Japan, we don't have. So Japan's probably the only one where we don't have the X-ray machines at the moment. I mean, of course, this could change in future.
Yes. Okay. All right. Thank you very much again, Nick, for your presentation. We have another coming up in 2 weeks, I believe. It's about the colorless diamonds on April 29th. So thank you everyone for joining today's session, and we will see you next time. Bye-bye.